All right, let's look at stoichiometry. Now, this should be very familiar to you in the sense of what we've done and what you've done in previous chemistry courses. I'm going to walk you through a little bit of each of these. So we have ideal, and ideal is everything's perfect to where you have no limiting reactant at all. Not realistic, but you could easily get one. Limiting reactant, more common, something runs out first. Molarity, so the idea is that you're using solutions, so those will need to be addressed, often done with limiting reactants. Gases, to where you're using ideal gas law, it can be ideal stoichiometry or not. Again, we can combine all of these things here together to get all of it. Now, we'll do later with enthalpy, bond energies, but for right now, we're looking at just doing some of the matter stuff, none of the energy. So, ideal. They want to see this setup that you have here, this what's called dimensional analysis. They often will look at, and that's how you get some points. If you just throw some numbers around and they can't figure out your work because it's not set up and organized with units and things, you're not going to be getting much aside from your 1 point for the answer. But again, this is going from grams to grams. You use your chemical equations, your molar masses, your mole ratios to get your amount. Watch your sig figs, they'll count for 1 point somewhere on there. It might be this one, it might not. You never really know. But these are the general guidelines that you have for any stoichiometry. It's a lot like conversions, but you got your mole to mole ratio that comes from your chemical equation. Now, limiting reactants, a little different. You're given values of both reactants. So you need to convert that to moles to compare. Now, there's a couple different ways you can do this. This is probably the most simplest, i.e. least to get confused. Let's call it that. So it doesn't matter what product you set it to, but the idea is that if you take the given amounts and convert them to the same product, you can compare which one is going to produce the least amount. The idea here is that if you had all of this H2SO4 being used to make this sodium sulfate, this would be the amount of moles. But you use the least amount, so therefore your reactant would be the least amount. An alternative way is to take one of the reactants and see how much of the other reactant you would need. That is valid. However, you have to then think about, do I have enough? Yes, I do. Therefore, the other one is the limiting reactant, or no, I don't. So now this other one I translated it to is now the limiting reactant. It's very confusing. Most students, when I've taught general chem and honors chem in 15 years, this way, they'll get right 8 out of 10 times. The other way, they screw it up more often than they get it right. So this is what I'd suggest. However, both always work. Now, once you've determined the limiting reactant, that's the number you're going to use to do all the other stoichiometry, always. When you have molarity, and we're not diluting here, but we're actually utilizing molarity, you have things like putting your unknown on the left and the other one on the right. So if I have so many grams, how many liters of that am I going to need? So the idea here is that we're converting from one to the other, so I know how many milliliters I would start with. So this is just the idea of molarity as a conversion factor, because I'm using the ideas of my molarity at 70 moles per liter to determine how many milliliters or liters I would need for this. Now, this is just a starting point because this isn't using any kind of stoichiometry at all. This is just using molarity as a conversion factor. You do the stoichiometry generally with the grams. You wouldn't use it with the liters, but you might be given the liters and have to convert it. This is just one example of using molarity as a conversion factor to get into the values you need to use with stoichiometry, which is at some point moles. Now, gas stoichiometry. This is where we use the ideal gas law to go from one to the other, moles to liters. But again, it's just another dimensional analysis, and then we need to use the ideal gas law to get there. So one way is using volumes. So if reactants are the same conditions, both gases, temperature doesn't change, nothing else changes, the volumes of the mole ratios are also volume ratios. So we would normally think 3 to 1 to 2. and we think of 3 moles of this, 1 mole of that equals 2 moles of this, we could easily say 3 liters of this, 1 liter of that, 2 liters of this. This might save you some time and effort when you're doing something like free responses, or even something as simple as multiple choices to where you have to do this kind of idea, but you don't want to go through the ideal gas law because that takes too much time, and they don't tell you all the information. So you can't do it unless you have it all. Another type, or again, showing this idea in action, when you have the 12 liters of hydrogen, you have a 3 to 2 ratio in order to get 8 liters of ammonia. A little more complicated idea, add STP. So STP, you have this ratio of 22.4 liters for 1 mole of a gas, any gas. So you can see if you're given 50 grams of the potassium chlorate and how much of your hydrogen you'd produce, grams to moles, moles to moles, and then we can go moles to liters to get that volume. You could equally do this using the ideal gas law. You need to understand STP, the pressure being 1 atmosphere, temperature being 0 degrees Celsius. If you plugged in all the same numbers, you get the same value. You can see this is a lot faster. A more complicated idea, how many liters, and you can see they give you different conditions than STP, would be collected from this. So it's good, same way off to here, only now we have a certain amount of moles. I can take that moles, plug it into my ideal gas law. We have moles, you have your gas constant that you're given. Remember to change that degrees Celsius into Kelvin. They're always looking for that good stuff. Atmospheres, dividing it, I get my 16.7. So these are the different types that come up as you come across with all of these. You're going to get plenty of practice. Again, you want to ask me any kind of questions that creep up. Yep, that's it. So, but again, very formulaic with this, and this is the work that would be expected to be shown. So practice it as we preach it, and you should be good. Let me know what questions you have. Catch you on the flip side.